SwayamPrabha. Digital India. Educated India.
In today's lecture, we are going to look at an alternative method to compute the effectiveness factor of a catalyst, and we will also look at external mass transfer resistance effects, which we have neglected so far. The way I want to do it is consider only two effects at a time, because in a catalytic reaction you have the internal diffusion, you have the reaction, and then you have the external diffusion. So, we looked at the interaction between the reaction and the internal diffusion. We will conclude that, and then we will go on to the interaction between the reaction and the external mass transfer. Okay. So, let me go to the differential equation. So, this equation basically represents the mass balance in a differential element inside a spherical catalyst particle. Okay. And this tells you that only the diffusive transport is there, and this talks about the first order reaction. What I wanted to do is, because this is a mass balance over a differential element, I am going to integrate this over the entire sphere. So, I am going to multiply this by the volume element, which is 4 pi r square dr, and then do this integration, which basically gives me and I am integrating this in the limits from 0 to r. So, I multiplied both the terms by this volume element 4 pi r square dr, and I am just integrating it from 0 to capital R. Now, remember, because of the diffusional resistance, the concentration of A is going to change with R, okay, and therefore, this basically tells you the net actual rate of reaction in the sphere. That is the right hand side. I am going to simplify the left hand side, noticing that I have r squared here, I have dr cancels with that dr. So, when I do this, I get dE times r squared dCA by dr evaluated between the limits 0 to r. This is my right hand side. Okay. Now, this quantity is, when I evaluate this at r, I will get d times, and there is a 4 pi times r squared times dCA by dr evaluated r equals r minus this quantity evaluated at 0, because I have r equal to 0 here, the second term is 0. So, this simplifies to only one term. This term here represents the diffusive flux of species A into the catalytic pellet. Okay. This is the surface area 4 pi r squared, dE times dCA by dr is the diffusive flux, and so this tells you the total amount of species A entering the pellet. So, the right hand side represents total amount of A entering the pellet, And so what this basically means is the total amount of A entering the pellet, it must be equal to the amount of A which is reacting in the pellet, okay, and LHS is amount of A reacting in the pellet. So at steady state these two have to be equal because there is no accumulation. Whatever is coming into the pellet has to react inside the pellet, okay, and that is what this is saying. So now the point is this effectiveness factor eta can be is the actual reaction rate divided by the reaction rate if Ca, the concentration inside, is equal to Cas, the surface concentration, whatever the surface concentration is. The point is, the numerator can be evaluated in two ways. The numerator can be evaluated using the right hand side, which means you solve the differential equation and then do the integration, or you solve the differential equation and thus carry out the differentiation. So this is much easier. Okay. Finding out the left hand side is much easier because all you have to do is differentiate the solution, evaluate it at R equals R. So this is the alternative method for calculating the effectiveness factor, okay, and this basically tells you that whatever is coming into the pellet, the species A, must be equal to the amount of A actually reacting in the pellet. So this is what I mean by saying the numerator can be evaluated either using the RHS, which is the definition, but the RHS is equal to LHS, so we can use this computationally. That becomes much easier. Now this is just to tell you that what I have written here is a macroscopic balance across the entire sphere. This is a microscopic balance written over a elemental volume of the spherical particle, okay. So that is the difference. I want to spend a little bit of time talking about the Thiele modulus or the phi squared parameter when we make equation unless we have which equation, the reaction diffusion equation, okay. We have phi squared on a dimensionless parameter which comes in, which scales as, or which is defined as k times r squared divided by dE. So dE is the effective diffusion coefficient because I say effective because we have the catalyst is made of porous network, so the pores are all tortuous, okay, and you can't use a direct diffusivity value, you need to take into account the tortuosity. So we have an effective diffusivity here. So like all dimensionless numbers, this also has a physical significance which I am going to explain. So this particular thing can be written as r square divided by dE divided by 1 by k. Now r square by dE I define as T diffusion, a diffusive time scale, and this basically tells you the time taken for species to diffuse over a length r. So I have length r and what is the time taken for the species to diffuse, and 1 by k is T reaction, the time taken for the reaction to occur, okay. This is the time taken for reaction to occur. So, if the reaction is very fast, okay, K will be very high, the rate constant will be very high, and the time taken for the reaction to occur will be very low. Okay. So, if reaction is fast, K is high, and T reaction is low. If diffusion is fast, that means D is high, the diffusion coefficient is very high, and T diffusion is low. Okay. The time taken for a species to diffuse is low if the diffusion coefficient is high. So, now if I look at phi squared being very much less than 1, okay, or phi squared low, what do I mean by that? I mean the T diffusion. So, I can look at phi square as T diffusion divided by T reaction. Okay. That means T diffusion is low. So, it diffuses very fast, the concentration of A, the reactant, diffuses very fast into the pellet, and compared to that the rate of reaction is very low, okay, very slow. So, here diffusion T diffusion is low, or T reaction is high. That means diffusion is fast and reaction is slow. Okay. T reaction is high, that means K is low. So, this is the situation where we call a reaction limiting process. So, here reaction is slow and is the limiting step, okay, in the limit of phi squared being very much less than 1. On the other hand, if phi squared is large, then T diffusion is large and T reaction is small. If phi square is large, then T diffusion is large and T reaction is small. Okay. So, that is, the T reaction is small, that means the reaction is fast. In this case, the reaction is fast, and the diffusion, T diffusion large means it takes a lot of time to diffuse. So, diffusion is very slow. Okay. Here diffusion is slow, reaction is fast. Therefore, here diffusion and internal resistance, internal diffusion is the rate controlling step. Okay. So, this is just to give you an idea about what the two limits are of phi squared. So, what is the rate determining step changes depending upon phi squared. So, now supposing you have a reactor, and let us say it is a catalytic reactor, it has catalyst in it, and the performance is not very good. You are expecting a lot more conversion, but you are getting low conversion. Then what you have to do is, you have to come back and look at the phi squared value. Okay. See, if in a low performing reactor, we analyze and find phi squared to be very much less than 1. Phi squared is very low, okay, and so phi squared is very low. That means the reaction is the one which is rate controlling, right? Okay, so the reaction is the one which is rate controlling. So what should you do now? There is no point in, the diffusion is already fast. There is no point in trying to make the diffusion faster because it is already fast. So what you should do is, we should increase the temperature to make the reaction fast, okay, or yeah, we have to change the catalyst. Those are the two things we have to do. So you have a system where you are not getting enough performance, and you do this analysis, find phi squared. Turns out phi squared is low. So what you have to do is, you have to change the catalyst or increase the temperature to make the reaction faster. So reaction which is slow will become faster. What about the other case? Suppose phi squared is much greater than 1, phi squared is large, then and my reactor is not performing properly, we have to improve T diffusion, make it lower, the diffusive time should be lower, okay. So what should we do? We should reduce size of the particle R, or increase dE by making the particle porous. So what you could do is, you want to reduce T diffusion, so you can make the particle more porous, improve the porosity of your catalyst, so that diffusion will be faster, or reduce the size of the particle so that it has to diffuse only a smaller distance, okay. So this will basically help you improve the performance of your reactor. So what I am saying is, this is basically to systematically tell you where is the problem, so that you can fix the problem and get a better performing reactor. I am not talking about a reaction pellet, we are analyzing a pellet, the reactor contains lots of pellets. How do you go about doing it? There are other challenges. If you reduce the size of the particle, the pressure drop will become higher, okay. So you have to look at the overall picture, but right now we are only looking at the interplay between reaction and diffusion. I want to talk about the next aspect, which is external mass transfer effects. So far, when I was talking about the porous catalyst, I was only considering the internal mass transfer, internal diffusional resistance. But like I told you, there can be also be an external mass transfer resistance, because of which the bulk concentration in the fluid passing over the catalyst will be different from the concentration on the surface of the catalyst, okay, because there is a mass transfer gradient, there is a mass transfer resistance. Typically, we model this mass transfer resistance in terms of a mass transfer coefficient, okay. So the point I am trying to make here is, like I said at the beginning, we are going to focus only on the effect of reaction and the external mass transfer, okay. So now we are therefore going to keep our life simple and look at a spherical catalyst particle which is non-porous, and I have a bulk concentration of A species A. This is my concentration of A in the bulk, and because of the mass transfer resistance, the concentration at the surface is going to be CAS. Because the catalyst is not porous, basically what I am doing is I am completely eliminating the internal diffusion, and the reaction is going to be confined only on the surface of the sphere. Okay. So, reaction occurs on the spherical surface where the concentration is CAS and the bulk concentration is CAB. Okay. So, the concentration of species A, the reactant, the bulk is CAB, at the surface is CAS, and there is a driving force which is going to tell you about what is the rate at which mass A is coming to the surface. So, and then on the surface you have the reaction which is occurring on the surface, and because occurring on the surface, I am going to talk about the rate of reaction per unit surface area. Okay. So, now the rate of mass transfer of A to the surface is going to be given by the mass transfer coefficient times 4 pi r squared times CAB minus CAS. Okay. The driving force is CAB and CAS is here. So, rate at which the mass is coming in is this. The rate of reaction on the surface is going to be given by Kr times 4 pi r squared times CAS. Okay. This is the rate of reaction, because and I am assuming again it is a first order reaction, and therefore, it is the reaction rate constant multiplied by Cs, and this reaction rate is defined on a per unit surface area basis. So, it is 4 pi r squared. Normally for homogeneous reactions we will define it on a per unit volume basis. Okay. So, this Cas, and this is the intrinsic kinetics. Okay. This is the what is called the intrinsic kinetics. So, basically in a reactor where you have this kind of system where you have non-porous catalyst and reaction occurring on the surface, supposing it is a steady state, whatever is coming into the surface must be equal to what is reacting at the surface. Okay. So, we have Kr times 4 pi r squared times Cas equals Km times 4 pi r squared times Cab minus Cas. Rate of reaction must be equal to the rate at which species is coming in. So, of course, 4 pi r squared is common, and you can do some manipulation. You can write this as Kr Cas plus Km Cas equals Km Cab. Okay. So, Cas is nothing but Km Cab divided by Kr plus Km. So, if you have a system where you know what the mass transfer coefficient is, and you know what the reaction rate is, and your reaction is first order, you can calculate what the surface concentration is going to be. Okay. So, this is the relationship between the surface concentration and the bulk concentration. Now, the bulk concentration is what you can actually experimentally measure, because that is what was feeding into the reactor. Cas is the dependent variable, okay, which is the concentration on the surface, which you cannot control. It is controlled by the interplay between the external mass transfer Km and the rate constant Kr. So, that is basically what it is. So, CAB is what we can control, CAS is a dependent variable, as if M is very much larger than Kr, then what can I do? I can write CAS as CAB divided by 1 plus Kr by Km plus 1. Okay. Km is much larger than Kr, so this will be very small, okay, and I can write this approximately equal to CAB. So, if Km is high, it means the mass transfer coefficient is high. If the mass transfer coefficient is high, that means there is no external mass transfer resistance, okay, because Km is high, and therefore, the surface concentration and the bulk concentrations are equal. So, here the external mass transfer rate is high mass transfer coefficient, and therefore, CAS is equal to CAB. I mean, this is an approximation, okay. But what about the opposite case? If Kr is much greater than Km, okay. If Kr is much greater than Km, then CAS is going to be, I can neglect Km, is going to be approximately 0. You can look at this, this is very large, I can neglect 1 in comparison to this. So, CAB divided by a large number, so I will get up almost 0. So, in this case, we have the situation where Km is very small, okay. The external mass transfer resistance is very high. So, the rate at which Ca bulk comes to the surface is very slow, the diffusion or the mass transfer resistance is very high, and whatever is coming in, and the reaction is very fast, the K reaction is very fast. So, whatever is coming to the surface is going to get immediately consumed by the reaction, and the concentration is going to be 0, okay. So, basically here mass transfer rate is slow, mass transfer resistance is high, and so this is the external mass transfer is rate limiting, okay. External mass transfer is rate limiting, and so the mass transfer is giving you very small amount of A. Reaction is so fast that as soon as it comes to the surface, it gets gobbled up by the reaction, consumed by the reaction, and the concentration becomes 0, okay. Whatever comes to the surface reacts very fast, and CAS is equal to 0, okay. So, this is the case. In this case, here So, here external mass transfer is rate limiting. Like we saw earlier, if Kr is much greater than Km, okay, what we have to do is, we have to, there is no point in increasing Kr because it is already high. So, to increase Km to get a better performance, okay, we must increase Km, and that could be because the mass transfer coefficient depends upon Reynolds number, Schmidt number. So, we need to flow the reactant at a higher rate, at a higher rate. And if K, this is R, no? If Km is much more than Kr, the mass transfer anyway is very high. So, I need to make Kr higher, okay. So, this is the reaction is rate limiting, then we must increase the temperature or change the catalyst, okay. That is what we need to do. We need to change the catalyst because that will improve my Kr. I need to increase the temperature to improve my Kr. So, that is what will take care of this. So, what I want to do is next talk about another small aspect which is equally important, which is intrinsic versus apparent kinetics, okay. The rate of the reaction is on a per unit area basis is given by KRCAS, because on the surface you have CAS and you have Kr as the rate constant. This is the actual rate of the reaction. Oh yeah, that is right. And you have Kr, and I can write this in terms of CAB as Kr plus Km. Okay. So, now this is why am I writing it in terms of CAB? Because when I actually do an experiment, I am trying to measure what is the rate of the reaction by looking at what is the concentration at the inlet in the bulk CAB and what is the constant coming out, okay, in the this thing of the reactor. And you will be doing some data fitting and all that, and you will try to estimate the parameter. So, what you observe is that this is like my K effective. This quantity here, Kr Km divided by Kr plus Km is like an effective rate constant. It considers both the effects of the reaction rate and the mass transfer coefficient, considers both Kr and Km, okay. And because of the external mass transfer resistance and the reaction rate which are coupled, Kr is much higher than Km, or let us do the ulta case, Km is much more than Kr. Km is much more than Kr, then the reaction rate can be approximated as, because now Km is much more than Kr, I can neglect Kr in the denominator, okay, and I will keep only Km here, and this Km will cancel with this Km, and the reaction rate will approximately Kr times CAB. So, in the limit where my mass transfer is very, very high, there is no mass transfer resistance, K effective here, K effective is equal to Kr. What you are measuring is the intrinsic rate constant of the reaction. So, you do your experiment, you try to estimate the K effective, which considers both, but because Km is much larger than Kr, you will end up measuring Kr directly, which is the actual rate of the reaction on the surface of the catalyst when there is no mass transfer resistance. Why is there no mass transfer resistance? Because Km is very high. Okay. So, K effective equals Kr, the intrinsic rate constant, as there is no mass transfer resistance. Here CAS equals CAB. Okay. So, I am basically, there is no mass transfer resistance, directly CAS is equal to CAB. So, reaction rate is Kr multiplied by CAB, that is my K effective. But supposing you do the opposite case, which is if Kr is much more than Km, okay, the reaction is very fast, mass transfer is rate controlling, then rate of the reaction. So, Kr is much more than Km. So, Kr is much more than Km. So, I will neglect Km, I will keep Kr here, and what will I get is equal to Km into CAB. So, now the external mass transfer resistance is the one which is rate controlling, okay, and therefore, what you are measuring, because whatever is coming to the surface is immediately getting consumed, it is very fast. What you are measuring is going to be Km. This Km, the mass transfer coefficient, now behaves like a reaction rate. Okay. So, here K effective behaves is equal to Km, or mass transfer coefficient is my calculated reaction rate constant. You are not measuring the rate constant, you are measuring the mass transfer coefficient. So, you have to be careful. So, what I am saying is, you have done an experiment, you have done your fitting of the parameters, and you find that some K effective here, but if it turns out in your problem Kr is much more than Km, okay, Km is very low, mass transfer rate controlling, you are not measuring rate of reaction, you are not measuring Kr, but you are measuring Km, the mass transfer coefficient. And that is what I mean by saying intrinsic kinetics and apparent kinetics. Intrinsic kinetics is Kr, okay, but because of mass transfer resistance, the rate constant that you are going to measure can be different from Kr. If Km is very, very low, you are going to end up measuring Km. If Km and Kr are comparable, if Kr and Km are comparable, you will measure Kr multiplied by Km divided by Kr plus Km. Okay. So, that is basically what you are going to measure. So, this is what I mean by apparent kinetics. So, this is an apparent kinetics. K effective, this is an apparent rate constant. this is an apparent rate constant, not the actual rate constant. Actual rate constant is Kr. So, when I said apparent kinetics and real kinetics, Kr is the intrinsic kinetics. Let me write this neatly. So, Kr is the intrinsic kinetics, K effective, which is Kr Km divided by Kr plus Km, is the apparent kinetics. Why is it apparent kinetics? Because it is getting modified by the mass transfer coefficient, and K effective is approximately equal to Km if Km is much smaller than Kr. So, this is simplifying to this. Okay. So, one has to be careful when doing experiments which are going to measure the kinetic parameters. That is the moral of the story. You think you are measuring the kinetic parameters, but you may end up measuring the mass transfer coefficient, or you may measure some other parameter which has the influence of both reaction rate constant and mass transfer coefficient. Okay. So, this is something which you have to keep in mind. Finally, I just want to say, in an actual pellet, you have if you have a porous pellet, you have the internal diffusional resistance inside the particle, inside the pellet, you have the reaction rate, and you have the external mass transfer resistance from the bulk to the surface. Now, what we have done is we have considered only two effects at a time. Reaction we have kept constant because we are talking about a reactive system. So, first we consider reaction with internal diffusion and spoke about the effectiveness factor. Now, secondly, we have looked at reaction with external mass transfer. We neglected the internal diffusion. So, we consider only either internal or external, but in an actual system you will have both. Okay, you will have both internal effectiveness factor, you will have external mass transfer resistance, and so you will have an overall effectiveness factor which considers both the internal resistance as well as the external mass transfer resistance. So, that is how you have to analyze the problem. We are not going to do that in this course, but it is just if you have understood the basic concepts, then you should be able to extend it to the case where the external mass transfer resistance and the internal mass transfer resistance can both be included to analyze the effectiveness of the catalyst. Thank you.